Welcome to another Great Car Basic demonstration, and I'm just going to talk about pulse width modulation, or PWM. So what is PWM? PWM is a generation of a square wave. Maybe I should change my frequency on my screen, but essentially it's a generation of a square wave that has a frequency and a duty. And what I'm going to show you today is how that frequency and duty is controlled in Great Car Basic along with clock sources. And so in Great Car Basic there's a number of methods that we're going to be using and can use. Some of them use low memory, some use more dynamic and use a bit more memory. But essentially I'm going to have a canter through those different methods and why they exist. So let me just show you what I got. I just saw my oscilloscope, it's hooked up there, and I'm also going to have an editor, the Great Car Basic editor, IDE here. So let's have a quick look through. So the first one I'm going to look at is what's called the legacy mode. And the legacy mode is made up of two constants, and these have been there forever. You change these constants of frequency and duty, and then you turn the pulse width modulation on, and you will get the result. Now I'm just compiling that code, and I will get a frequency in my oscilloscope. Currently, that's not bad. It's got a max of 38. There we go. It's settling down into 38 kilohertz. That's exactly what I wanted, and a duty of 50. And it's as simple as that. So if you want a fixed mode, that should work on all chips because it was intended. It's the legacy mode. There is a constraint with this. It only supports CCP1 and only timer 2. So if you want to use timer 2 for something else, you can't use this method. So what we've got is another method. And it's a later method. And it means that you can use CCP2 and it has a multiple timer source. But you need to give it, because it's got a multiple timer source, you need to be able to give it some more parameters via the constants. So I'm going to, in this case, use CCP module 2, and I'm going to set it to a cycle frequency of 40, a duty of 20, with a clock source 4. So there are three constants. I've just shown it on the screen. I'll highlight those in a moment once we get the result on my oscilloscope. And here we can see we've changed the frequency to 40 and a duty of 20. And so let's recap. I've got CCP module 2. This particular chip has many different modules, but I've selected number 2, and I'm setting the clock source for this channel, number 2, to clock source 4, and that clock source 4 has been set to 40 kilohertz with a duty of 20. And if I want to change it, I would simply change these parameters, these two constants, and it's very low memory. The code is highly optimized, and you could use the optimization code to reduce the number of bytes, but it won't give you it won't give you a lot. And as you can see, we've got the result here. So let's have a look at that method enables you to select different clock sources here. Okay, and all you've got to do is set up the frequency for each clock source. So you got clock source 2, 4, or 6, depending upon your device. So let's look at number 3. Option 3 is actually interesting. It's a legacy command, okay, and but it's a method, and the method will use more memory, and you pass it 3 parameters, and I'm going to pass it the channel number, the frequency I want, and then I'm going to pass it because it's dynamic. I've got it hooked up to my ADC here. And I don't know what it's set to currently, but we'll find out on the screen. So it's a method, and because it's a method, it uses more memory. So I'm going to rotate the pot here on my right hand side, and we will get changes. You can see that the frequency is set, and it's dynamically changing the duty. And if I turn my pot right down, I will get nothing. Quite correct. If I turn it full on, we'll get a high. If I put it somewhere there, I'll get a value. Now, so you can actually pass it 3 parameters: the channel number, so the 1, depending what your modules are. You have to look at the specification. They're numbered 1, 2, 3, 4, 5. I think there's 9 you could have in here, 1 to 9, different frequencies, and then you can pass it the duty value. And what's important about that, it is using more memory, but we have a snippet that will help you optimize these things, and you can just come into here, snippets, optimization code. You can stick it in there. Now these are all the optimization codes for ADC. Let's just delete those out of the way because we don't need to optimize it. Oh, in actual fact, we could optimize the ADC. Yeah. I'm just going to set this all to false, and then the only ones I'm going to be using is ADC1, which is true. Set that to true. I'm using CCP2. I would always recommend, by the way, that you get your code working before you optimize. Don't even try. And then we're on channel 2, and we need clock source 2, because this can only use timer 2. All right, okay. So currently we're at 826 words, and it does ramble inside of there. Okay, and it's using 826 because we're doing ADC as well. Okay, all right. 569. If I turn the ADC off, I guarantee if I just put a static value there of 127, which is, ooh, oh yeah, unbalanced braces. You've seen that before, hey? So this is just doing now a 50%. There we go. And it's now using 519. So it's coming down and down and down. So you can optimize the code. Okay, let's look at, so this one here is a dynamic method. If you need a dynamic, use this. If you don't, use the static. Okay. Fixed mode. Number 4. I'm just going to pick up the right piece of code here. Number 4. Staying with the CCP channels, if you wanted to change the clock source, because remember previously it was stuck on timer 2, you need a new command. Okay, so you need this command, which has got H pulse with modulation CCP timer n, and you can specify your timer source at the end. It's as simple as that. Okay, so I'm gonna I'll set that to 42, bit of a random number. You can see the optimization code sitting beneath it. I did that earlier on, and this is using a different clock source. Oh, now luckily my optimization code is set to 2. If I set that to 4, my clock source down here is set to false. I have not tried this in my pre-run of this demo, so let's see. I'm not expecting anything because my clock source is not valid. There we go. Let's put that to on, turn that to true. Now you don't have to do the optimization code. If you've got a part with lots of memory, don't worry about it, okay? But always get your code working before you optimize it. Alright? And there we go. Already I can see it up on my scope. We're getting what we expect. So this command supports different CCPs modules, 1 to 9, and you pass it at different clock sources. Some chips might support 2 and 4, other parts might support 2, 4, or 6. Okay. Well, it gets a little bit easier now because some parts, devices, microcontrollers, have a specific PWM module, and those modules are different from the CCP modules, and therefore you need to give them different command sets, etc. And we support that in fixed mode, and it's the same command. It's the same constant. You've got to specify your frequency, your duty, and then your clock source, and then you need to put PWM module behind it to force this PWM command to say I am using the PWM module. Okay, so let me look at make sure we've got some different numbers in here. I'll put that to 44. I'll set the frequency to 44, so we just know that things are happening. So this one is now using the PWM module, not CCP. Okay, this part has everything. Okay, so I've got a frequency of 44 and a duty of 44. That's not bad. That's with the integer. I mean, this is pretty good stuff. So you can change your clock source 2, 4, or 6. You can then specify. Now, therefore, on this particular part, I've got a CCP where I can use pulse width modulation at certain frequencies, and I've got this pulse width modulation at certain frequencies. But you've got this timer. You can't overlap. If the timer is set for one, you can't be using it in the other side. But you've got different uses and different options. Okay, so that's static mode for the PWM with multiple timer sources. You can just specify the timer source, and then you've clearly got a dynamic method. Okay, my little slidey here has not been updated. If I take you back to slide number 1, it is actually the last one is PWM dynamic. It has multiple timer sources, and you have quite a lot of parameters you can pass it. Okay, so let's just bring that all up now. This is number 50. Now, I'm going to give it a value here of 50. It's actually 127 represents a byte value, therefore it'd be 50%. I'm now giving it 4 parameters, and here I'm talking to the PWM module, not the CCP module, because I've got 4 parameters. Okay, that's a simple way of thinking about it. I've got a channel number. Oh, now look, I got PWM4, so I put a 4 in here now. I'll show you a cheaty way of getting this, of you understanding this stuff. Some of the newer chips, 4 parameters. You could put 5 in actual fact, and the 5th parameter would be the resolution. You can actually pass it a 10-bit value as well. So here we've said it's a 30%. I've set it to a duty of 60, which is puzzling my little brain here. I've got a minimum here. What have I got on my scope up here? A duty of 60%. That's because it's taken it as a word. So if I wanted to do something clever in here, I'm going to take that there, I'm going to put it inside of my do loop, because I'm going to make it dynamic. I'm going to do a read AD on AD0. I'll do a wait for 5 milliseconds, just because it's nice. Let me think if that will work. I put this value behind here when you weren't looking. I'll put that back. Recompile. It's dynamic now. What I mean by dynamic is that I've got a pot on it, and if I change the pot, I get different values. There we go. So we've got many different methods, but this is the cheat sheet. Legacy mode PWM is the command with its parameter, if you need it, for the PWM module. Okay, and that will give you a low memory fixed methodology, and then you use these methods for the dynamic modes, and that's a really simple way of thinking about it, and it's taken me an hour or two to figure that out. Okay, that was a demonstration of Great Cloud Basic, pulse width modulation demonstration. I'll call that a wrap.